Welcome back everyone to the course on topological phases of matter. So, we are now entering into what we call week 2 or chapter 2 rather. And the first chapter, I hope we have built enough foundations about what is topology and how to write equation of motions and calculus on topological space or topological manifold, and also how to deal with fibers. And for us, that the fiber that we are interested in are the wave functions, which belongs to a Hilbert space. Okay. Now, we are going to apply those methods on. We will start with how topological space are generated through magnetic field in 2 dimensions, 2-dimensional space, and how topological phase appears as some of the phase that we are already know and we have already studied in different way, but now I want to connect those things to topology. And this is what it was in the original content of the course, in which we will study Aharonov-Bohm phase or Peierls phase, and these are all with magnetic field. And how these phases are related to, or rather Aharonov-Bohm phase is related to something called a magnetic monopole. Okay. And then we will talk about quantum Hall effect, and this pretty much is the first thing that gave us the idea of topology in condensed matter, although this was done in I think 1980s. I am forgetting the exact date, probably 84. Although the Aharonov-Bohm effect was slightly earlier, but the connection to topology was not very clear. And also there is something called a Dirac monopole. The setup was proposed by Dirac monopole, and that was also there much earlier. And through quantum Hall effect, we realized this topology is somehow connected to H states. Okay, because when we created a topological space in our condensed matter system, we had a periodic boundary condition, and that's how the topological space was obtained, and that led to topological invariants. And now, once we remove that boundary condition, the periodic boundary conditions, we sort of change the topological space. So, there has to be consequence on the physical observables as well, on the topological invariants as well, which will the topological H states. Okay. And there is also something called a charge pumping, in which, as we sort of, okay, we will talk about that. I think it's a little too early to talk about the given example, and also Laughlin argument about the charge pumping and also Thouless pumping. And then we will talk about TKNN number. It is a topological invariant. So, what these 4 gentlemen did is that they showed that the quantum Hall effect that we generally study, if you put a periodic boundary condition on the Landau level problem, then we actually get topological bands, and then we can define a topological invariants in the band, which are sort of homotopically equivalent to Landau levels, Landau quantization, but one can compute it in the momentum space rather than real space. And that was kind of the first paper that connected the topology, the concept of topology that is involved in the quantum Hall effect. Okay. So, these are the lecture notes which are there on archive. You can look it up, and Sakurai books as well, and also these things are also there in the other books that I have already said at the beginning. And if you have forgotten, just look it up, the Landau level problem. I need those, and probably also Brood model. for semi-classical transport. All right, let's start with that's a person's name, Peierls. Let's say I have some magnetic field, or it's even you can define it without even defining the geometry. So, suppose I have a magnetic field in the system, and we have learned that the momentum operator, which is defined by the gradient operator, change to momentum operator and the vector potential. And now we know that vector potential and the momentum operator is something called covariant derivative that we have defined, and the covariant derivative that acts on the fiber where it is wave functions. And we also obtain such a covariant derivative or a canonical momentum from classical mechanics as the conjugate variables to the momentum, and you can see that they both are very similar thing. Okay. So, with that, so if I have a charged particle of charge, let us call it minus E, okay, and under some magnetic field B, which is denoted by the vector potential A. Okay. This is a quantum mechanical problem. So, we get I h cross delta, which is the partial derivative d mu, the component of nabla being, and then the connection, and here the connection being E by C. Earlier we used Q and then vector potential. This is the canonical momentum operator acting on psi r. Now we can solve it, and we can solve it, and we know how to solve it and what sort of phase we get, but let us recast the problem into something that we know. So, something we have studied. So, let us say we are going from some initial point to final point, and we have some curve, right, from some r0 here to r under this magnetic field, in which some magnetic field is there. Okay. Now, instead of solving it, we can just use a parallel transport. So, the psi at r is transported parallelly from r0 right. This is our parallel transport P. Okay. So, it depends on r and r0, and in principle it should also have the path. It depends on the path it took, unless different paths are homomorphic, homotopic, that we will talk about later. So, path ordering. All right. And this is the quantity that's called, let me put the I, called Peierls all right. So, it is a phase that is acquired. So, the wave function's amplitude has not changed, but it obtained a phase as it travels from one place to another place under some magnetic field. Okay. Now, let us consider a loop. So, the electron has passed through under this loop. Let us call that loop is at R 0 and let us call it rho, the loop that we usually talk about. So, now and we do have this spiral phase. Okay. And let us take C equal to 1 for simplicity. Let us also put C equal to 1, and so then what we will have all right. So, this is kind of a vector, this is a vector potential, and we are integrating over the potential modulo some constant, right. So, as the electron moves around here and come back, does it gain any energy, does it release any energy, because we have some vector potential, and this is where comes to conservative force or not. So, if the magnetic field is here, and let us put the magnetic field in some solenoid, so it is confined within this region only. Okay. So, we will make it all right. So, now you see that in this region there is no magnetic field, but it still sees the vector potential because of the field lines. And as we know that if you have not enclosed a magnetic field, there is no work done. So, this will then become 0, as you, and that is equivalent to saying that we can contract this loop all the way to 0 and you get no work done. So, this loop or this phase is nothing but 0. On the other hand, if I draw another loop from the same base point, now we enclose this point. What do we get? We will get this phase, but on the other hand the electron has to be single valued, right, because it closed a loop and we are talking about something like a cyclotron motion, right. So, that this will keep on moving around this point, this magnetic field, this solenoid. So, something has to be conserved, and we will talk about those conserved quantity like angular momentum, or whether exactly the angular momentum is conserved or not, and how the angular momentum is conserved by adding the flux that is passing through it. We will talk about that, but let us just assume that the electron is just going around this loop. Okay. And how many times, and whether all many times it goes around corresponding to the going around once, they are homotopic or not, we will also talk about that. But for this case, it is a loop, and we can just use the Stokes theorem as we did. What we get is this S is the S that is enclosed by this. Okay. So, this is nothing but the magnetic flux. Okay. And you can define this to be 2 pi by and this is the magnetic flux and this is the flux quanta. And this is very small, and the value is so centimeter square is a big area, and this is the amount of magnetic field that passes through. It's a very small quantity. So, it just counts how many magnetic flux divided by the flux quanta that passes through. Okay. And in this case, the magnetic flux, the first loop, the red color loop, the magnetic flux is 0, although it sees the vector potential, but in the second case the magnetic flux is not 0, but it counts how many magnetic fluxes it passes through. And since this phi has to be 2 pi n, because it has to the electron has to come back to itself and has to have only a phase which is 2 pi times n. So, this phase becomes quantized. Okay. So, now what exactly we did, why these quantizations happened, and what happened here, why there is no sort of a quantizations that is not there. And what we have done is that in the first case we had a topological space which was R2, right, just a 2-dimensional space, but in the second one we actually changed the topological space. And once we turn on the magnetic field, rather, we have changed the topological space. Why? Because R2 is made of all the coordinates, all the points, but now I need to worry about the solenoid, which is not included in R2, right? Minus solenoid is my new topological space, and this topological space is not same as R2, and that is now defined by this winding number n. If the electron goes around, it now has a phase that will be 2 pi times n. Okay. Whereas here it will always be 0 in this case. Okay. So, here in this case whereas for this case z, and that z being this number. So, phase is something that how do you determine the phase, and this is what the Aharonov-Bohm effect is. They created a setup experimental setup So, it is like a double slit experiment, but with magnetic field. Okay. And what I do is that we have some magnetic field in a solenoid. So, this magnetic field is only confined within this region. Okay. And now, if my from some source electron, and then I will have some detector, okay. This is my source, this is my detector, and let us call this path 1 and this is path 2. Let us call it S1, S2. So, as the electron passes through path 1 and path 2, and then you take a linear superpositions of those two, it should be able to, I will show you that it is equivalent to forming a loop from here and there, and that should track whether it has seen a magnetic field or not, and that is how one should be able to determine the Peierls phase. Psi 1 from phase 1 and R being, let me complete this. So, here I am denoting R, and let us say this is my R0. Okay. So, both started from some R0 with some parallel transport, where this is minus E by H cross R0 to R, but in S1 path. The same thing, but in a different path, and as we talked about earlier that this phases or parallel transport are path dependent. So, what you can do is that we can reverse this path, and let me just do it quickly. Before that, okay. So, one was this path 1 and another one is this path 2. Now, we reverse this to going the opposite one, and let us call it S2, which will denote that I am going backward. So, what that would do is that I will get a plus sign, and let me highlight this with minus S2. I will get a plus sign. Common, I will get 1 plus e to the power minus I e by h cross path 1 and then going backward. So, I will be able to make this entire loop path 1 minus path 2. Okay. In fact, you can have the initial states to be even different, and that will give you some ratio, but here we are only interested in this one. Peierls phase. So, you will get an interference pattern now due to the Peierls phase. The interesting thing is that both the electrons has not experienced the magnetic field, but it knows the, but it is getting still affected by the magnetic field, because it actually has changed the topological underlying topological space by creating a hole here through which a flux is passing through. All right. And how does it see it? It sees it through the connection, which is the vector potential. So, it sees the vector potential, but not the magnetic field, and now it tracks how much of magnetic field we are, and the phase that it accumulates, and which we can detect through the interference pattern here, would be corresponding to how the magnetic flux is changing. And there will be homework to show that a similar effect can be obtained through electric field as well, but you have to use the gauge properly. So, now comes to what is kind of something that is unique about this experiment in this phase compared to any other kind of a magnetic field, because what is unique here is that we have confined the magnetic field in a small region, and the quantum particle is going around it, but not seeing the magnetic field. And what from the electron's perspective, it is seeing the magnetic field as some sort of a monopole, and the vector potential it says as some sort of a vector potential coming from a monopole, not a scalar potential like the electric field would be, but it is a vector potential, but at a monopole. So, monopole means it is a single point, and from where it is diverging. So, when a field diverges and you have a monopole that is confined somewhere here, so it should diverge in a way that as you take the surface integral, it should remain constant. So, that means the magnetic field has to vary as 1 over r square, because the area scales as r square. So, if you want the area multiplied by the field to be constant, so the field must vary as 1 over r square, and indeed that is what is happening. Okay. So, that is the unique thing about it. So, we have created a setup in which we have a gauge field that is unique, and we will call it singular, and that gives us monopole, and we meant magnetic monopole, and also something related to gauge obstruction. And we will talk about what it is. We know that magnetic field is arbitrary with respect to a gauge transformation, and here obviously those principles will be valid, but there is a twist in this story. Okay. So, what we have done is that let us take some two-dimensional space and in which the magnetic field is passing through some solenoid along z direction. Alright, this is where the magnetic field is confined. but otherwise inside, whereas B0 outside. And now we have an electron see, and here the base point does not matter, and this is the setup. And let us keep, because all these curves or loops are sort of homotopic, so whether you contract and expand it does not matter. So we can fix it to be some radius r. Okay. Equal to 2 pi n, and let us fix this radius to be 2r. So we will have r. So that means, and this is a line integral, and we can do this line integral then, and let us call it d phi. This arc is d phi r. Is the arc length, total arc length, a phi equal to. So we choose a gauge such that the magnetic field is phi directions. Okay. So we get a phi n by 2 pi r, okay, phi 0 here is the flux quanta, right? And if we obtain the magnetic field, which will be along z direction, you will find that magnetic field will scale as okay. In fact, if you do it completely ferric, okay, let me start with C and then we will go back to the R. Okay. So now I see that it scales with 1 over r square. So it is a singular here, at r goes to 0, it diverges, and then it is radiating as 1 over r square, such that it is like a monopole charge which is radiating with 1 over r square. And then if you take a solid angle anywhere with at any r distance, the total r will be 4 pi r square, and you will see that the flux will be conserved, which means we can define write it much like how we write electric charge, 4 pi r square, and G is in phi 0, which is n h by E, monopole charge. Right. So it is like the magnetic field radiating. I mean, here in this 2D it is going like this, magnetic field with vector potential defined like that, and okay, so magnetic field is going like this. But now you can generalize this problem to 3D as if some point charge is sitting here, some point magnetic monopole charge is sitting here, and you can do this integral. You can convert this line integral into a surface integral, and what you will find is that it just measures the amount of flux we have. which of course we will be able to get it from some surface as you go around it. And if you compute it, of course, it is 1 over r square, and then you will have the theta integral or the phi integral will give you. Oh, let me just do it. Solid angle, and this integral, so this cancels, and you will have 4 pi, which will cancel with this one, and you will get, and minus comes as a right because it sort of comes from the fact that these are electrons. So it's kind of the magnetic field is kind of, from the electron's perspective, the magnetic field is sort of coming towards it. Okay. So we have, so from the electron's perspective, as if there is some sort of a magnetic monopole charge, and magnetic monopole is kind of a singular spin, if you like, kind of a magnetic monopole, which is sort of radiating all the directions. And we have denoted it with the vector potential, but this vector potential does actually something funny here. Okay. So how do we see that? So it's a monopole charge that we have already talked about, and that gives you the flux, magnetic flux, but and we sort of gone from 1D in which the electrons are moving. Now we sort of say that that is equivalent to having some solenoid charge sitting there at a given point, and you take a surface integral over it. And if you actually go into now a 3D, what sort of a magnetic potential that would correspond to? And I will show you very quickly. So there are so I am talking about some point in which a G charge is sitting, radiating, and I am defining some S2 around it. Okay. The radius does not matter, you can always contract and all. So for this, on the surface, the vector potential, and you can take an answers and verify, the derivation is slightly harder, and what we will see is that, so this is my north pole and this is my south pole. We will see that you cannot define a single vector potential all over the place. You have to at least define 2 vector potential. Each vector potentials are arbitrary with respect to some gradient or some scalar potential, but if you choose one gauge and then try to define a vector potential that will be smooth everywhere over the surface, you will see that you will not be able to do. Let us take an answers and verify that answers gives the monopole formula that we have obtained, but it is not one connection. So on the north pole, we will see that you can write it as 4 pi r 1 minus cos theta by sin theta. So this is this additional theta and phi dependence I have added compared to earlier, which was a 2D one. I take it as an answers and verify that this gives you the monopole charge 4 pi r square. Okay, radially. So now you see that this vector potential is smooth everywhere including at north pole is smooth, means differentiable everywhere, and I am not talking about r equal to 0 because the r equal to 0 is a monopole anywhere. Anyway, this is smooth everywhere I have including at the north pole which is what I am defining as theta equal to 0, but not at south pole which is at theta equal to pi, where it diverges. So, you do not actually have a single gauge that is smooth everywhere. On the other hand, you can define this will be smooth at theta equal to pi, but not at theta equal to 0, and both will however give you this. So, what it is telling us is that if I have a monopole, the space which I am now calling R3 or S2, it does not matter in this case, it is actually a topological space, and it is a non-trivial topological space, because I really cannot define all points mapped to R3 smoothly. I need to at least have two different charts. So, this topological space we need at least two different charts. In one chart, which I can choose the chart to be defined from the equator to the north pole, or if this can be shifted, but at least I need two charts. One that will include the north pole, but not the south pole, and the second one which has to include south pole, but not the north pole. And for two different charts, we will have two different gauge field, vector potential or connections that will give you the right topological invariant, which is in this case is just the monopole charge, but you cannot have a single one. Each of them are arbitrary. You can add a function and you can change it, but what you cannot change is the difference between them. That will come out to be g by 2 pi r 1 over sin theta. Okay. And this is called the gauge obstructions. So, in all the topological space we will talk about, we will study, we will see that the wave function cannot be defined on a, we cannot fix the gauge to a single gauge field. If you can do that, then there is no topology, things will be trivial topology or trivial space, but if there is an obstruction to fixing the gauge, then we do have a topological space, and that is related to having multiple charts. Okay. So, we will stop today here, and from next class we will start quantum Hall effect.